So, hello everyone. Welcome. Oh yeah, sure. It's closer. So, hello everyone. Welcome to joining our ITS seminar this week. My name is Jerry Sun. I'm the system manager at ITS-Irvine. So, today's presentation is given by Dr. Yiqiao Li. The title of her presentation is a real-time track characterization and monitoring system through the integration of advanced traffic sensing technologies towards Freight Mobility Living Lab, FML2. So I have worked with Dr. Li for more than 5 years in the same research group, and she's a very talented researcher. The system really hard. Yeah, she works really hard. Yeah. And the system she's going to talk about is actually the backbone of this freight facility, the freight mobility living lab. And she spearheaded the design and the implementation of this system from ground up. So without further ado, let's get started.
Okay. Thank you, Jerry, for the introduction. And thank you everyone for coming. And feel free to grab some pizza if you feel hungry, right? So I think I need to share screen, right? So today I'm going to give you a brief introduction about our the current work that we have in our group. So it's mainly a track real-time. We designed a real-time track characterization system through the integration of advanced traffic sensing technology like loop detector, like the things you probably know, the LiDAR sensor. And today I'm going to show you how I build up the system from the modeling part, the edge computing, the data, the information communication to the live demo of the real-time detection results. So for today's presentation, there will be two parts. The first one is the real-time track characterization and monitoring system. This system was built up using a loop detector, which is widely deployed across California. And in this part, we'll go into details about how the data was collected at the edge sites and how the data was processing, and also the communication architecture, how they transform back to the ITS server, and finally how they are saving in the database. And I will show you a live demo about the real-time detection. The second part is how I utilize the roadside LiDAR sensor to provide you a detailed truck profile, and further using this information to classify truck and further enhance the overall freight mobility living laboratory system. When you're talking about truck, people may just thinking it's a huge thing. And back in 10 years, people are more focusing on the length of the truck, because using loop detector, you can somehow measure the length of the truck, right? And as the people doing research in the truck, people are more focusing on the some detail parts. For example, the axle classification, counting the number of axles. Based on this truck, you can see there are 5 axles and the tractor-trailer truck, right? And people using this information to evaluate the pavement design, how this type of truck are harmful to the pavement. And also, an important part of the truck is its body, right? As you can see, this is a dump truck. And usually this type of truck is transporting some of the waste. So understanding this type of information will give you a better view of how the commodity flow in the network. So this is also something we are looking into. And the second part, and the third part is the GVWR. Based on the brand of this truck, you see this is a Western Star 4900, right? And based on this information, you are able to know this is a Class 8 heavy-duty truck, which have disproportionately negative impact to the environment. So we are thinking of build up a system using inductive loop to be able to classify those trucks based on different classification schemes. And here is the detailed introduction about the FHWA axle-based classification, the GVWR classification, and the body type classification. More and more people interested in what body type they preserve, and the commodity flow on the freeway. There are two approaches we are thinking of using. One is the existing loop detector system, which is widely deployed across the US, right? And we're trying to leverage this kind of existing infrastructure, like the loop under the pavement. And we use the advanced detector card attached to the loop so that we can retrieve the information from the loop and get a detailed truck profile. And using this profile, we do some feature extraction modeling process so that we can understand what type of truck it is. And this is the basic field setup I will go into detail in next slide. And another one we are thinking of is using advanced emerging technology like ALPR sensor, the license plate reader, so that we can tracking the truck in the network. Also, the LiDAR sensor, it gives you a really detailed side profile of the truck so that you can classify them in relatively high accuracy. And here is one of our test bed with the ALPR camera here, and also the control cabinet and the video camera pointing towards the travel direction so that we can get the ground truth results. So that in this case, we can use the ground truth label to develop further develop the model. And then to whom do not have background knowledge about the signature data, usually based on some of our classes, we know that when the vehicle is traversing the loop, you will be able to see a binary signal, right? If we implement this advanced detector card, which gives you a higher resolution, like 1,000 samples per second, you will be able to see a detailed vehicle pattern. Like you can see, this is a single unit pickup truck, right? And based on their binary signal, you won't be able to see what's the difference, right? But after increasing the resolution, you'll be able to see the detailed pattern, right? And also for this different type of truck, they are associated with different body type class. They fall into different body type class, axle classes, also the PVWR classes. So it's really hard to find a harmony between those classification schemes. So that's why we were thinking of put them individually and customize a different model to serve the needs of different classification schemes.
Yiqiao, can you clarify a little bit those acronyms?
Huh?
For example,
the
PVWR and the previous slide, the AP.
Oh, I mentioned that ALPR is the automated license plate reader.
Got it.
And this one is the gross vehicle weight rating. So which defined by the manufacturer of those vehicles. Here's the basic system setup. This you may see in some of the highway, right? This is a loop detector under the pavement, and it will attach to the control cabinet. So we replace the conventional card with the advanced loop detector card so that we can get a detailed signature pattern, right? And also, interestingly, we also explore the use of Raspberry Pi, which is a single board computer. I will show you. Today I bring it here. So it's a really lightweight system. So we're using this type of single board computer on some rural highway which have a lower volume because it won't be able to handle that much traffic, right? But this will reduce the price of the field unit by like 100 times. It's but by 10 times. So it's $70, and for general field units maybe $600. So this is something new progress we have in the current project. And also, additionally, for the major freeway, we are using a solid state field unit. So we don't want to get too much dust in the computer, right? We have a bandless unit in the cabinet. So it's pretty, in terms of the computation, it's only an i3 computer. So it's capable of handling the signature data. It's sufficiently capable of handling that much signature data with the limited computations. So what we do is, for example, when you see a vehicle passing by the loop, this is a vehicle, and it will generate a signature pattern, right? And then we do a interpolation to extract the key feature of the signature pattern and use this pattern to classify trucks using a sample of machine learning algorithm, customized algorithms to be able to predict the truck types. Like we were able to get the truck body type, the axle-based classification, the GVWR classification. Also, one of our paper introduced how we calculate speed using this single loop detector. And all of them will be sending back to the ITS server. So now the interesting part is how we build up the communication architecture. The basic communication protocol I was using is called MQTT. It's kind of a base of AWS. So it's a vanilla version of sort of like that system. It's sufficiently used for our research data collection. I deployed a MQTT message broker on the central server so that it can manage the queue. When the edge computing unit communicates with the central server, it kind of subscribe and publish the based communication. So when the central server is subscribed to those field units, those field units will sending the information, the classification results back to the server. And as you may see, it's a hierarchical topic design. So when you adding additional sensor into the system, then you will easily adapt those process. So it's pretty flexible system. Also, I do some encryption on the communication side, so that just prevent people trying to hack into the system. And then this message broker will also serve as a publisher. It was sending those information to some of the WebSocket that I will demonstrate later. So to be able to see the real-time results. Also, one part will be archived to the database. And so we have already saved a lot of statewide signature data so that we can use for different transportation applications. Are you?
I want to share.
Okay. So this is a track activity monitoring dashboard we create to visualize the real-time detection results. And so after subscribing the message broker, we are able to see the live detection result across the Southern California. So this is what's happening right now in the network. So the blue ones are the passenger vehicle and the red one are the trucks. So you will get a better sense of how the truck is distributed over the network. Also, I adding additional feature for this web application. So when we select the truck only mode, those are only trucks, and the blue ones are the single unit truck, and the red ones are the semi-trailer trucks. And also suddenly you will see some of the green points, maybe along those rural highway. Those are multi-unit trucks.
For the GPS data, installed in the truck.
No, this is a loop detector results. So when the vehicle passing the loop, you will be able to see a live detection here. Yeah. And then I will show you a sensor integration site that we have right now, but the problem is there's some communication issue between our central server and this field unit. So this is what I'm trying to. This is one of our detection sites. We have a LiDAR sensor here, and also a video camera for the ground truth. Also the live detection. See the vehicle passing by and it's capturing us in close line correctly, right? So it's a really cool tool to demonstrate the real-time ability of the system. And then here is some case study of this research. Like we use some aggregated data. This is like 1 week of dryage truck, which is a 40-foot container truck. So we aggregate the results to see how it's distributed over the network. So you can see this is I-710, which is kind of a gateway of the container ports. You will see a really dark color in here, which demonstrate they have a larger dryage truck population. And also the radius of the circle tells you how much truck traveling across these corridors. It's easy to see some of the difference, like some rural highway, you won't be able to see too much dryage truck, right? And some of the LA, some of the essential corridor around the LA port will give you a lot of dryage truck movements. It's transporting the goods between the local port and the warehouse. Additionally, we do a case study on using the GVWR results. And this is an aggregated result, tells you the distribution of light duty, heavy duty, and the medium duty, which it's an essential input for the emission model, so that you will get a better sense of which is the emission hotspots across the network. This is a really interesting result. This result is from a Raspberry Pi, and this small thing is running over 1 month. The results over 1 month. It keeps running without any disturbance across the whole month. Based on this result, it's a new way to collect the FHWA classification counts and saving a lot of money. So the second part is related to the LiDAR research I did during my PhD. So the basic idea is we find that those inductive loops are widely deployed across the major freeways. But for some of the rural highways, there is implementation problems to deploy some of the sensors. For example, as I mentioned, there's a if you want to add in additional intrusive sensor over there, you have to do some lane closure, maybe causing some of the safety hazard to the workers, right? So we were thinking of using a mobile solution to be able to get the track data along those freeways, on those rural highways. And here's a key timeline for the LiDAR-based vehicle classification. Initially, people are using a single beam laser sensor, so it's scanning through the a cross section of the road, and to get the to get the profile of the truck of the vehicle. But the problem is that it's pretty costly if we put a sensor high up to the alongside the roadway. And in 2009, Koifman used 2 LiDAR sensor to capture the vehicle traversing the detection zone, and using this 2 sensor to kind of stitch the frame between stitch the LiDAR frame together to be able to get a full side profile. The main use of this data is for the lens-based classification, because you won't be able to get too much details from this type of sensor. Until 2010, Google began to test the self-driving car, and they start to utilize a sensor, a rotating LiDAR sensor, which is putting on the top of the autonomous vehicle to perceive the ambient environment. And then researchers thinking, oh, that's a great idea to get the profile of the truck. So they put the sensor vertically to scanning the each slice of the vehicle, as you can see in this graph. But the problem is it's compromising the field of view. So what we are thinking of is put it horizontally, like what is displayed on what is placed on the autonomous vehicle, and then thinking of merging multiple points together to get a really detailed truck profile to extract more truck related information. Oh, one more thing, people also use the horizontal placement, but the problem is, you see, this is a passenger vehicle, right? But the point cloud is too sparse to see what type of vehicle it is, right? So this is the classification framework that we built. So first of all, we will, because after one LiDAR scan, you will see the truck and the foreground truck and the background environment all together in one single frame, right? But the environment information is not something we need. So the first step is we're just extracting the foreground tracks using some traditional image processing method and using DD scan to group them to detect those objects, and further using the data association algorithm to identify those trucks belonging to one single truck, because when the truck is passing by, there's multiple frames, right? And then we're thinking of since this has a multiple frame and it's kind of capturing its characteristic from multiple perspectives, why not just merging all of them together and then get a detailed truck rendering, 3D rendering. So this is our this type of method generally used in robotics to, for example, one moving robots is traveling around one object and getting the point cloud from multiple perspectives and then reconstruct them, so that you have a better understanding of the object, right? But what we are doing is the LiDAR sensor is static, and we capture all the moving objects and merging them together. So here I want to go into the details about the reconstruction. So basically, we are trying to merging two consecutive frames together, right? So like a point cloud A, point set A, and point set B. We are trying to align them using a transmission matrix. So there's basically two types of algorithm that we can use iteratively getting the transmission matrix. After getting the transmission matrix, then we will be able to know how to transform the target frame transform the source frame to the target frame, right? So the basic idea, the basic algorithm.
Can you clarify a little bit? What is the blue curve and the standing for?
That's one point set called P, another point set called Q. So you can relate it like truck frame A, truck frame B when you're passing by.
So the same truck, but two frames.
Yeah.
I see.
So we want to firmly align this point cloud together because they are looking at the truck at a different perspective, right?
Got it. Is it from different sources or just from
one single LiDAR?
Same LiDAR.
Yeah, the same LiDAR.
Two frames.
Right.
Yeah. Can I ask what's the reason for two frames happen? Why they have two frames?
It's just an example. It's just an example. So you have a multiple frames.
Oh, do you have multiple?
Yeah. So this is I think I need to move this a little. It's just the introduction about the point cloud registration.
Got it.
So just to simplify the truck point cloud to.
I think you could minimize the video bar.
Mm-hmm.
Yeah.
Oh.
So people do clarification.
Yep. And then. And then when we're trying to minimize the distance between two point clouds, there are two methods. One is intuitively, you can calculate the difference between 2 points, corresponding points, right? Another way is trying to calculate the source point, the distance between the source point and to the target plane, how to reduce the distance and so that they can firmly align. This is basically the objective for the to calculate the transmission matrix that I mentioned in the previous slides. So this is the overall step we did. So just like what Sumei was asking. So when vehicle is passing by, you will have a multiple frame, right? And this is the detection zone. So sometimes you will see the tractor parts of the truck, right? So we think those are kind of redundant because ultimately when you go in closer to the LiDAR sensor, you will be able to see some of the point on the front part of the truck, right? So we just the first step is trying to improve the computation. We exclude some of the leading frame and the trailer frames.
Oh, can I ask how long is one frame? Like 0.1 second?
Oh, yeah, you mean the resolution of the sensor, right? It's 10 frames per second.
10 frames per second.
Yeah.
So we're trying to merge those frames.
Yeah.
Got it.
So to exclude those frames, I set up a threshold, like if this frame is only taking the 20% of the whole body of the truck, I will exclude them. And those are middle frame that could be useful for the truck reconstruction. Here's some of the pre-processing steps we did. Some statistical outlier removal based on the distance between, for example, we take 50 nearest neighbor and exclude some of the points which have 2 standard deviation away from the selected points to exclude some of the statistical outlier. And also another step we did is downsample the overall frame. Like you can see, it's buckle the point cloud into the 3D pixel. We call it voxel. So we buckle those into voxels so that we get somehow the noise, the point at the tractor parts, right? You can see some of the noise are aggregated into some of the voxels. Basically, there are pre-processing steps. So when the truck is first entering to the detection zone, you will see a really sparse point here, right? So here we use the point-to-point distance because it's pretty sparse, and to align those 2 point clouds. And the second part is we find that when the vehicle is leaving the detection zone, it will form a really large area of the plane. So in this case, the point-to-point may fail because the point is mostly distributed on the plane, right? So in this case, we're trying to do some fine registration to further align these 2 points. This is the improvement results. And then different from other applications, the transportation, we believe that the truck is moving on the ground plane, right? So during the optimization process, we constrain the transmission matrix so that the truck is just traveling on the YZ plane, XY plane. So here's the here you can see this is the 2 frame together. It's the adjacent frame aligning together, and this is the multi-frame accumulated so that we get a really dense point cloud for each truck. Right, so I think this may answer Sweet's question.
Can you elaborate with the x-axis and y-axis? Oh,
it's just because it's a Cartesian space. So you have a point. We will know the x, y, z location of this point, right? It's basically the coordinate. Yeah. So here's some results of the reconstruction. As you can see, single frame may not be able to give you a really detailed lower profile of the truck, right? But for some of the reconstruction, all the reconstructed trucks, the profile is pretty clear. And then utilize the reconstructed point cloud. We were thinking maybe the definition of FHWA classification is based on the lower profile, right? Whether the general body type and how many axles they have, right? So we're thinking we're just extracting the lower profile and then use this lower profile to fit into some of the predictive models. Let us say maybe deep neural network or some of the lightweight machine learning algorithm to classify them. So what we did is creating a sliding window so that to extract the lower profile of the truck and then smooth it. After smoothing the lower profile, we extract the 100 data points and use those as to represent this pattern and use this pattern to classify truck in detail. Like you can see the front wheel and the tandem wheel in the back, right? It's pretty clear after the reconstruction. So this is the overview of how the model is developed. So we extract the multiple frame and then merge them all together to get the reconstructed point cloud. Yeah. And then extracting the lower profile, finally fit into the neural net and using ensemble to be able to increase its generality for the model. Here's the final result. It seems like the result is pretty cool, but we do find some of the issues. Like this is a precision value. Precision value means the denominator has a false positive value. If you see a really low precision value, you will find a really high false positive, which is something we don't want. We don't want to generate a lot of.
Can you clarify what is false positive?
It's for example, it's not there, but you predict like that. Yeah. So that's something we don't really want. So this is some space we want to improve our model, even though they have a really good recall value, but the precision gives us alarm to further improve the model. And here's the model is doing a great job on classifying some of the, for example, class 9 and 10. The only difference between these two classes, class 10 have additional wheel on the back. So it's class 9 is 5 axle and 10 is 6 axles. So for some of the traditional method, it's really hard to differentiate this kind of scenario, especially using inductive loops. I will mention that later. But for the LiDAR-based model, the lower profile give you a clear view of the rear wheel so that you can classify them correctly. So here's the final result compared with the state-of-art model using single frames. Currently, I will not say it's a fair comparison because they are missing some of the classes. But based on, I think based on visual verification of those lower profile, we are pretty confident saying that we are able to classify them because of the reconstruction process. And then we are thinking, okay, we have a really dense point cloud, 3D reconstructed point cloud. We can also, visually, we are able to identify what type of body type it is. So we're not using this reconstructed point cloud to classify those tracks based on their body type. But the problem is the body type is no longer looking at the lower profile of the tracks. So we were thinking maybe we need to focus on the global feature of the overall point cloud. So we need a detailed class, and what feature should we use for this type of problem? And and those models should be irrelevant to the line changing, because if you do a line changing, you get a distortion of the point cloud. How do you you need to find a framework so that is irrelevant to some of the other factors like what I list here. So we are thinking of using a representation learning algorithm, which is end-to-end learning framework. So we just using the point cloud, the whole point cloud itself, and fit into the neural net structure for training, and finally get the results. And the PointNet is what we finalized for the task like this. It's a first neural net architecture that's directly using the point cloud as the inputs. The previous one are using, for example, they buckle some of the point into the voxel and using those voxel as an input, just like an image, to classify them. But the PointNet simply using the raw points as an input. And this paper was 2017, and after that, we can see some of the object detection method is built up upon the PointNet. For example, using PointNet as a pre-trained feature extractor to and adding some detection heads to detect the vehicle in the point cloud. And what we did is this is a reconstructed point cloud, and we do down sample to random sample, extract 1024 points of the reconstructed point clouds and normalize them, finally fit into the neural net. And during the training process, we do some data augmentation, like rotating the point cloud along the z-axis, so that it's the model knows whatever direction is going into, it doesn't matters, right? So also to also augment during the augmentation process, we introduce some of the Gaussian noise in the training process, and this is a computation units that we are using for training and testing. And after the training, after the model training, we find something interesting. So for example, if we apply a single model, we'll ultimately get different accuracy value, right? Recall value, the correct classification value. So should we believe that that's a true performance of the model, right? So that's why I plot the prediction band for 10 different models to see the variability of this model prediction results. So we find some of them have, for example, in close one, they are kind of dominant, right? They have a lot of observations. The bar plot you see observation, the counting number, the testing number, the testing samples in the data set, and you see a really small variance for its prediction results. So probably it could caused by the imbalanced data set issue, or some, for example, you have a lot of variability, but you have a limited training sample, also can cause issue like that. How to address that? We just we just ensemble of multiple point nets, so that and average them to get the final results. Here is how I select the ensemble numbers. The rule of thumb from some of the textbook is like 5 to 10 ensembles, and I run over all the 10 model ensembles to see when the model will give you, the ensemble model will give you a lower variance and a higher mean accuracy, mean correct classification value.
Oh, Yiqiao, elaborate a little bit the ensemble model. I'm wondering, our audience might wonder if
it's using the model results, and it's averaging the model results. For example, we train the model. Basically, we are using bootstrap aggregating ensemble, like here. Oh, I don't have the graph. But they basically you train several models with different initialization. They will give you different they will give you different model weights, right? And different model weights, we consider that's a different model. And using those, apply those different models, finally we do the averaging of the results we believe that results is more reliable than any other single models.
Got it.
Okay. And here's this is ensemble.
Yeah.
And here we are basically using a simple moving average. Also, we try some Bayesian approach, like trusting the likelihood value that's given by the model prediction. But it seems like the simple moving average, a simple model averaging approach is there's no significant difference by using the Bayesian approach and the simple model averaging approach. Here's the final results for the body type classification. So as you can see, using the reconstructed point cloud, we are able to achieve pretty high. This is the correct classification value, which is a recall value. So the true value over all the ground truth value, right? So we are able to classify. I think there's 30 different truck types. And after we developed the LiDAR-based model, we were thinking, LiDAR is pretty expensive, right? Loop is cheap. LiDAR give you a really detailed truck profile, but Loop give you a one-dimensional signal, right? How can we leverage these two together to be able to automatically upgrade our system? So the most difficult thing is we don't know what neural net were thinking, how they classify those vehicles, how they classify based on those patterns. One thing we can see is just checking the pattern you are using. Here's the result. You see this, both of them are enclosed one, but one is class 8, one is class 9. So they share pretty similar signature patterns, and similarly, the class 10 and 9 have the same issue. So it seems like the signature is trying to understand the general body types and then infer their classification, their FHWA classification. But we don't know. We just it's just based on visualization. And for the LiDAR, we see it have a really clear lower profile. So it probably understanding the axle number, but also we don't know. So what should we do? One thing is just a visualization to see. This is a human intuition perspective. We think the model is understand in the way that we are understanding things. Another way is using interpretable machine learning algorithm framework to interpret what feature the model is trying to highlight. So the deep neural network model, everybody loves it because it has a really good performance, right? But it's a black box, lack of interpretability. But some of the simple linear regression is easy to interpret, but lower accuracy. So people are proposed a unified framework called the sharp value, and using the sharp value to highlight the point that the model is recognizing this could be the key point to understand this this whole either lower profile or the signature pattern. So I calculate the sharp value for across the this is a signature and this the lower part is different. It seems like the sharp value is highlight all across the body. So it's trying to understand the whole body, based on the whole body to understand what type of track it is, right? But for the point cloud, the sharp value is central to see this is a tendon value, a tendon axis, and this is a single axis, right? It's trying to look at the axis like what we think it is, right? So we were thinking, maybe in the future, the axle-based classification, the loop-based classification may be outdated because, for example, you change the design of the whole overall track body, and the model is trying to bias towards and understand the body itself. So in this case, the axle-based model needs to be upgraded, right? This is the basic idea. But for LiDAR-based model, you're just looking at the axle. So how can we use the LiDAR data to label the signature data so that it automatically upgrades the overall system? So we have strategically deploy some of the LiDAR over the network and using those integration sites to upgrade the axle-based model. And then based on our communication framework, we can upgrade all the model to statewide. Here's basically the structure of the self-learning framework that we propose. So we are, for sensor integration side, we are trying to use the LiDAR results to label the signature, and using the labeled signature to using the labeled data to retrain the signature model so that you can upgrade it. Luckily, we have data back in 2012, so we are able to do some experiment on that. So this is the data set which allowed us to do experiment that I mentioned previously. So I do find that when I'm trying to apply a model developed in 2019 and to the model to the data that collected in 2012, there is a significant drop for the class 7 vehicle, and which quite makes sense to me because some of the most of the class 7 vehicle are vocational trucks. So it's kind of a location specific. So maybe you're trying to develop model in this size, and the transferability won't be as good as other different type other classes because the type may change across multiple sites and multiple years. The design may change. So it's a really good indicator saying that this approach may help. And here we are using a transfer learning framework because we don't want to retrain the model after collecting more, right? So what we did is using the previous fully connected layer like a feature extractor so that we don't need to train the overall network. I mean, this is still a lightweight model, but in the future, the concept can be transformed, right? So I fixed the several layer at the very beginning of the network and changing the layer to see which performs better, which have a better performance on the data in 2019, and how to balance the accuracy value, the performance on the a new data set and the old data set. So it's gradually locking the layers, freezing the pre-trained weights of the neural net. So in this case, after using this as a feature extractor, we just losing this set the weight free here, and then using a small data set to retrain the model. It's just tuning the parameter here. So it will be a really light way to resolving problem like that. And here is the balance between the number of fixed layer and the performance on the old data set and the new data set. We don't want to compromise the old data set. Also, we don't want to overwhelm the new data set, right? So here's the final results.
What do you mean by old and new?
Oh, which one?
So you mean old data set and new data set?
So one data set collected in kind of 2019. Yeah, I think this one shows the results. A small newly collected data set is referring to 2019, and others are some of the data collected back in 2012. Yeah.
Got it.
So, and then this is a balance between the performance on the old data set and new data set. And then based on the results, we are able to see that we can rely somehow, based on this experiment, we can see we can somehow rely on the LiDAR labeled data, because you don't see too much. Some of them are based on the ground truth data labeled trained on the ground truth data. Some of trained on the LiDAR labeled data and the performance comparison. So using this framework can allow us in the future, we don't need to go into the field, upgrade the system once again, and LiDAR can access the loop results. Yeah. Yeah, that's basically it for my presentation today.
Does anyone have any questions?
I have a quick question. So I'll let you get through some first. For the upgrade data, what do we mean by upgrade? So,
it's kind of labeled using LiDAR data and then train on the LiDAR labeled data set. So it's an upgraded data, upgraded model.
Yeah, I know that. But you mentioned the left-hand side, the ground truth data.
The ground truth is visual is accomplished through the visual verification, and the LiDAR labeled is label the data using LiDAR results. Yeah. We use the LiDAR results as a label for the signature data training, the signature model training.
Yeah, answer my question.
Okay, thank you.
I actually have a question. Okay. So when you were doing the point net, so after all those efforts of combining all those frames into a dense point cloud, why do you have to drop some of the points and randomly pick a fewer number of points to fit into the model?
First, it's because of the training. You cannot use a lot of feature support without emphasis on certain features, right? So you cannot throw everything to the model, and you will be really computation inefficient way. And then I think what you're trying to ask is why not just using single frame?
No, I was trying to see if you have any way to pick the
essential point.
Yeah, the essential
point. Yeah,
so
that's
with more information.
Yeah, right. That's because we are using PointNet is an end-to-end learning algorithm. So it's doing the feature selection during the training process, different from the traditional method, which you have to extract by yourself and then using the feature that you think is good for the model and fit into the model. So this is two different approach. So PointNet is basically a random sample from a 3D rendering the point cloud, and then you don't know which one is essential. You just throw everything. Yeah.
Yeah, but maybe there are a way to like try multiple folds because each random peak will give you different results, I suppose, right?
Yeah.
You start with medium points, but you shrink down to 1024.
Yeah,
yeah. Right?
Yeah. So
would that make a difference if you try different runs?
Okay. Instead of trying to resample the data, what we are doing is using the jittering the points using a Gaussian distribution. So basically, one round of training won't take the same point cloud. So it's kind of another augmented point cloud that you fit into the network. Instead of resample it, what I'm doing is using augmentation approach. Yeah.
In the reconstruction and classification, how much the error do you think comes from reconstruction? How much error do you think comes from classification? Because the final accuracy is a combination of those two, right?
Yeah.
How much error do you think comes from reconstruction? Because that is also an estimation of what is actually the point form of the clock is. So how much of error do you think estimate the?
Yeah, for this model development, we didn't consider the construction error because we do another round of ground truths to visually verify whether they are reconstructed correctly or not.
If you create points based on the ground truth, create actual points for each classification, or run it through the model, how do you think that error would go down?
What do you mean?
Instead of taking the 10th point, I don't know how you take a point, the graph where you take
the profile
of the graph from the reconstruction. Instead of taking it from the reconstruction, if you take it from what actually you know how the points are in actual system.
Yeah, we don't
do that. Do you think the error would go down a lot, or do you think the error would go down a little bit?
I currently don't have a number for that, but I do believe that could go down pretty significant because I think
so you believe most of the error comes from the estimate reconstruction.
I wouldn't say it's come from the you mean the contribution of the reconstruction? Yeah.
Okay. And if you don't use reconstruction, because it seems like it's going to be computationally pretty expensive.
Without
reconstruction, it sounds like it could take a lot of time computationally. If you don't use the reconstruction and find points from frame, which you can track and use that.
Yeah, we are. Yeah, right. We are currently working on that because we are trying to. This one was using a traditional method to extract the point cloud, right? So currently, I mean, autonomous vehicle, they are doing the same thing, but they are not classified vehicle in details. So some of the model like point pillar, which use PointNet as a backbone, they are trying to. The final result is you get the detection, the bounding box, and you know the classification. So they take these two values into the training process. So it's based on single frame.
Because at the end, you're only considering the axis. So why even think about reconstructing top half of the frame?
Top half.
Like the entire truck. If you're only going to consider like axis of the feature point straight on, why not just avoid top half of the frame? So
it's giving you more information to make it reconstruct firmly. So for example, if you only have information in the bottom part, probably they will get some distortion after the construction results. But you know some of the gap here and some of the gap here, you get a full sense of this truck, and it's helping you to get a better reconstruction results.
But do you think that computation is worth the effort, worth the accuracy level?
The balance between these two, right? Yeah, that's a really good question. So it depends on the application. if we want to archive those data and get a really good classification results and use that for self-learning, then we use this approach. And if we just want to get a real-time results, then we just using single frame. Could be sufficiently give us the information that we want. Yeah.
Yeah, I think the top half of the data is also essential for some classifications, right? Whether you have a sleeper or if it's a platform, what type of cargoes you are carrying, also has an impact, right? So,
yeah, he mentioned it's a lower profile, so the actual base, but also this theme part is also essential because it's based on axle itself and it's a general body configuration, somehow considering the general body configuration. So you do need some information like that.
Yeah, thank you very much for the very informative presentation. And so I have, maybe some very basic questions for the LiDAR data. What is the, frequency?
It's 10 frames per second. 10 frames per second.
10 frames.
Yeah.
Okay. So did you guys know the, for example, position or pixel? You guys eventually are going to map those pixels into position, right?
Yeah, we need a GPS data. So one of the projects, the Blue City project, they know the location of the sensor. So and also the coordinates, so you will be able to calculate the location of that point.
Okay. So you have some like a reference point.
Yeah, the reference points.
So then, what is the accuracy of this position? Because
for this study, we don't have a GPS data installed, so we won't be able to know at this point.
Yeah, but in general, the accuracy of the LiDAR should be within several centimeters.
Several centimeters.
Yeah, for distance measuring should be within several centimeters.
But I suppose because of the depth, right? I mean, because this is kind of like more like 3D. The intuitively the area will be larger when we get to further away.
Yeah, I think so. And also during data capture, we also noticed that it's also being affected by even temperatures or refractions, like the air density changes, that also affects the measurements. Yeah, like when you have when the temperature changes largely across the day, the measurements actually shifts a lot because the air density changes and it affects all the light travels.
This leads to another question. I understand that compared with loop detector data, definitely second provides more complete picture of the plot of the cars. So basically, loop detector data, if works well, can give us that, but it's also under a lot of assumption. For example, relative constant speed, right? But for this one, it sounds like there is potential. Could you get a 3D image of the car or just 2D? Because 3D is very important, but the height versus the
length.
You kind of get my question.
Yeah.
So when you reconstruct it, are you guys interested in reconstructing the real 3D image or just 2D?
It is 3D in nature, actually.
Yeah, right.
But due to the angle, you actually see more points on the sides, which are physically and most of the points on this side are missing. So you are more like seeing like half of the box, something like that.
How do you separate the edge between one face versus another dimension? You kind of, I see some potential challenges there, and
yeah, if you have some raw data, you can show that. You can show them in the 3D in the point cloud viewer. Show them what the one actually looks like.
I'm wondering, shall we dismiss the audience from online?
Oh yeah, sure. I think it's about time. So if you have classes or anything, you need to leave early. So you can be like, but we can keep the discussion going on if you have any questions.
So we can wait for this is a roadside LiDAR. You can wait for a vehicle passing by.
Okay,
yeah, if you go to
Center shadow.
Yeah, the shadow was generated by the yeah. Can you change the view, like let's go from top view so that you can see the width of the vehicles.
Or you can change
the angles. Yeah, this everything is 3D. But of course, you come.
Is this live or
this is
live?
Yeah, this is live.
Yeah,
that's cool.
I will look at how the speed of the vehicle would affect that classification.
Yeah, we did an evaluation on constant speed and some acceleration, deceleration. There won't be too much effect. Statistically, we did an evaluation on that.
If you can classify the speed before reconstruction, can't you be like if we can take a range of speed, one frame would be enough to
get the speed for
classification, because a specific range of speed would have similar frames.
Yeah, but based on different angles, that is right. Sometimes you won't have a complete view of the vehicles.
Yeah.
In certain frames.
So the bonding
you will see the front face and the back. And yeah.
I have a quick question with regard to the third research. The third research, we're trying to use the LiDAR data to frame the model. But how accurate is the LiDAR classification results?
Oh, we showed in previous slides. So. Here's the LiDAR classification results. So, and also I did a comparison, just like the last slides, compare the LiDAR labeled data and the training results of the LiDAR labeled and the ground truth labeled.
Yeah.
So it doesn't seem too much degradation. But the problem is my concern for this research is we don't have a sufficiently large data set to cover more variants of the truck types. Whether this is kind of biased towards the certain truck type, that could be a problem for research like that. So I do have a concern for these results.
Yeah, a quick question for 0.89. So this is using for the LiDAR 0.89 average.
Oh, okay, yeah.
Yeah, the bottom is 0.89.
Yeah,
go back to your previous slide, then we could see the accuracy for your LiDAR classification.
Yeah, because this is a partition in different way. So there should be a little bit slightly difference between the accuracy value, but in the same scale.
So this one, the accuracy is even lower.
Yeah, but because of different initialization, you will ultimately get slightly different results. And what I did was using ensemble to reduce the variance, and so that they are falling into the same level of accuracy. So there should be a little bit different. And also the main problem is they are not training in the same data set. You cannot get exactly the same answer for.
Got it.
Yeah, but they are in the same scale.
Got it. How accurate can LiDAR predict like classification? Then 90% or 80%?
Yeah, it depends on if you are looking at the average results, this is an answer. And also you may see some of the classes have a pretty somehow low accuracy, right? So it's kind of depending on your target, you evaluate this model in different ways. Accuracy, correct classification rate, F1 score, they are not the only thing you are using for evaluating things. It depends on your applications.
Yeah, I understand. Any questions from the audience? Online. Yeah, online we have Lu.
Did she say something?
Do you have any questions?
Okay, I think that's it. Then we can thank Dr. Li for the presentation.
Okay.
I think we also could take a good picture.
Oh yeah, sure. Yeah.
And